the last video, we had this theorem that said that any totally bounded metric space, any sequence in a totally bounded metric space has a Cauchy subsequence. That is actually an if and only if statement. And for the sake of completeness, I'm going to state it, I'm going to prove the converse. So I'm going to state it as an if and only if statement. So let's let XD be a metric space. And then XD is totally bounded. That is true if and only if every sequence of points in X has a Cauchy subsequence. We proved one direction of this last time. Now you're going to see the proof of the other direction. And we've seen, we saw one direction on the previous slide. So let us go ahead and we'll prove just the other direction. So we've seen that if XD is totally bounded, then every sequence has a Cauchy subsequence. So now let us prove the converse. So we're going to suppose XD is not totally bounded. And then we're going to try to build a sequence with no Cauchy subsequence. What does it mean to not be totally bounded? Then that means that there exists a positive radius such that you can't cover X by finitely many balls of radius R. So if N is finite and X1 up through Xn, if those points are all in X, then X is not a subset of these N balls. So the idea is that you can't cover X with finitely many balls. Okay, now what we're going to do is we're going to build a sequence with no Cauchy subsequence. So here's how we do this. We're going to just pick our first element. A1 is just any element of X. And then we construct this sequence inductively. So what that means is that if A1, A2 up through AN-1 are chosen, then N-1 is finite. So by definition of not totally bounded, X is not a subset of the union up to N-1 of the ball centered at AK of radius R. And let's name this set Xn. Then we just pick An to be any point in Xn. or that is not in Xn. And if X is not a subset of Xn, well, the reverse inclusion is true. Xn is a union of balls in X. So if Xn is not covered by Xn, there must be some leftover point. So here's the picture of what's going on. You pick your A1, you draw a ball around it of your fixed radius r. Then you pick an A2 somewhere else in the set. You draw a ball of the same radius up to the limits of Professor Barton's drawing ability. And you just keep going. You keep picking new points. And drawing a ball around them of radius r. And the idea is that you will never run out of points. You will never cover up the entire set, because if you did, well, that contradicts our non-totally boundedness assumption. So this is how we're building our sequence. And it should be pretty clear that this sequence doesn't have a Cauchy subsequence. And let's make that rigorous. If n is bigger than k, then an is not in Xn. So an is not in the ball centered at ak of radius r. So the distance from an to ak is at least r. So, and on the other hand, if k was bigger than n, we could make the same argument in reverse. So if n is not equal to k, then the distance from an to ak is at least r. And then any subsequence this is still true. The distance between any 2 points in the subsequence is at least r if j is not anytime j and k are unequal. The only time they're within r of each other is if they're equal. So if the subsequence was Cauchy, then at some point they'd all be within r of each other, and they aren't. None of them are within r of each other. So this sequence is not Cauchy. The subsequence is not Cauchy, so the parent sequence that has no Cauchy subsequence. And that is all there is to that. Now I would like to discuss Cantor's theorem, which is something we saw last semester. So, for those of you who do not remember this perfectly, which in reality is all of you, let me rewrite this. Cantor's theorem says that if you've got a sequence of sets And we're going to say that they have to have the following properties for each n. Suppose that so first off, we're subsets of the real numbers. And we'll talk about how this works in general metric spaces in a minute. Second off, none of our sets are empty. Third, your sets are all closed. And fourth, your sets are nested. And then there are two conclusions, which I'm going to call conclusion A and conclusion B. If one of the sets Fn is bounded, then the intersection of the Fn's is not empty. And the second conclusion is that if the diameter of the Fn's, which you remember is the largest distance between 2 points in Fn, if that gives you a sequence of real numbers, of non-negative real numbers, and if the diagonal converges to 0, then the intersection, not only is it non-empty, I can tell you how many points it contains, and that is exactly 1. Now, of course, we'd like to generalize this to arbitrary metric spaces because we kind of want to do that with everything in Chapter 1. So here are two theorems in your book. I am going to give you the short versions of these theorems, and then I will write out a longer, more precise version. So theorem 5.3.18 is that part B holds. That is the obvious generalization of part B to an arbitrary metric space if and only if the metric space is complete. And I want to emphasize that we only need completeness. We do not need totally boundedness. Now, diameter is going to 0, so in effect we have a regular boundedness, but we might not have total boundedness. And here is theorem. Your book calls it a corollary and only proves one direction, but I'll go ahead and call it theorem 5.5.7, and that's that part A holds. In XD, if and only if now, since it's chapter 5, you're probably expecting me to say XD is compact, but the original Cantor's theorem is in the real numbers, which isn't compact. So we'll write this as every closed bounded subset of XD is compact. Then if XD is compact, then every closed subset of a compact set is compact, whether it's bounded or not. Actually, it's just that they're all bounded, so you don't need to bother checking that. And this holds in slightly more. So here is theorem 5.3.18 in a little bit more detail. Let's let XD be a metric space. Then XD is complete if and only if for all sequences of sets with, let me write it down, Fn is a subset of X, Fn is not equal to the empty set, Fn is closed, the Fn's are nested, Fn contains Fn plus 1, and the diameter Fn converges to 0. The set the intersection of all the Fn's contains exactly 1 point. So let's prove this. Let's start with the direction where XD is complete. And we'll pick one such sequence of sets Fn. And I really don't want to write down all the conditions, so we'll just say they're written there. And for each n, let's let x sub n be a point in f sub n. Then the xn's, they form a sequence in X. Claim it's a Cauchy sequence. You knew Cauchy sequences were going to show up sometime the minute I said complete. So here's how we prove that. We pick epsilon greater than 0, and let's let n be such that the diameter of Fn is less than epsilon. Then if n and m are both bigger than n, then xn is in Fn, but they're nested sequences, so Fn is in Fn minus 1 ... F big N plus 1 eventually is in F big N, and xm is also in F sub big N. So the distance from xn to xm, these are 2 points in F big N, so this can't be any bigger than the diameter of f sub big N. The diameter of f sub n, remember, is the supremum of the distances of every possible pair of points in Fn, which is less than epsilon. So our sequence is Cauchy. So xn converges to x for some x in x, because x is complete. All right, now if n is a natural number, then this sequence, the sequence of xk starting not at k equals 1 but k equals n to infinity, is a subsequence of the main sequence. I'd better index that by k because I'm using kn for something else. So it converges to the same number. I don't think we've proved explicitly that subsequences in metric spaces converge to the same thing as the parent sequence, but we did prove it in the real numbers back in section 1.3, and the proof carries over exactly the same way to metric spaces. Also know that at xk, just as before, that's contained in the set Fn. Xn is in Fn, Xn plus 1 is in Fn plus 1, which is in Fn, and so on and so forth. And Fn is closed. So we have that x is in Fn for all n. So x is in this intersection. So the intersection contains exactly 1 point. At least 1 point, sorry. You can check pretty easily that it is exact. If y is in the intersection of the Fn's, then x and y are in Fn for all n. So distance from x to y can't be any bigger than the diameter of Fn. And since the diameter is going to 0, the distance from x to y is 0. So y and x are the same point. And so we've seen that the intersection, we've seen that it contains at least 1 point, and it can't contain any other points. So it's a singleton set, and that's what we were trying to prove. Now let's prove the converse. So let's go ahead and name this condition. And as usual, we're going to name it star. So let's suppose that the condition star holds. And then we want to show that x is complete. So of course we grab a Cauchy sequence. and we want to prove that our Cauchy sequence converges. And of course, we're going to need to use this condition star, so we're going to need to construct a sequence of closed sets. Well, first off, we're going to let this set be the set of all xk where k is bigger than or equal to n. Wait a minute, that is not closed. So let's call that set En. It might not be closed if our Cauchy sequence, for example, doesn't include its limit. And since we need a sequence of closed sets, we're going to let Fn be the closure of En. All right. And then what do we have? We have that Fn is indeed a subset of X. En is contained in Fn, and En is not empty. So Fn is not the empty set either. And Fn it's the closure, so it is indeed closed. And that's 3 of our conditions. Now we need to show that the Fn's are nested. So first off, let's observe that En plus 1, that's all the xk's where k is at least n plus 1. That is clearly a subset of En. So the closure of En is a closed set containing En plus 1. It's a closed set containing En, so it contains its subset En plus 1. So by the definition of the closure, remember the closure of En plus 1 is the smallest closed set containing En plus 1. It is the intersection of all the closed sets containing En plus 1. We have the closure of En plus 1 is contained in the closure of En. So the same thing is true. So we have that Fn contains Fn plus 1 because they're the closures of En and En plus 1. So now we just need to figure out what the diameter of Fn is doing. So I think I am going to leave it as an exam study problem. The closure of E has the same diameter. The diameter of the closure of a set is equal to the diameter of the set you start with, since you're only adding limit points, which necessarily are very close to points you've already got. So we'll leave that as an exercise. So that gives us that the diameter of Fn is equal to the diameter of En. So to show that the diameter of Fn goes to 0, we just need to find the diameter, show that the diameter of En goes to 0, and we'll do this directly using the epsilon delta definition of limit. Let's let epsilon greater than 0 and let n be the natural number in the definition of Cauchy sequence. Let's say if m and k are both bigger than n, then the distance from xm to xk is less than epsilon. Then if n little n is bigger than big N, then distance from xm to xk is less than epsilon for all m and k bigger than n. So that's true for all, by definition of En, that's true for all xm, xk in En. So diameter of En is less than epsilon. Strictly speaking, it's less than or equal to epsilon because we are taking a supremum of things that are less than epsilon, but you can work with that. So the conclusion is that the diameter of Fn goes to 0. And then we've seen that this sequence of Fn satisfies our condition. So let's let x be the name of the point in the intersection. That is, by our condition star, x, a point in x exists. And then we have that. And now it's not too hard to see that x is the limit of our Cauchy sequence. So pick epsilon greater than 0 and let n be such that the diameter of Fn is less than epsilon. And we can do that because the diameter of Fn is going to 0. And then if little n is bigger than big N, then xn is in En, so it's in Fn. So, and x is in all the Fn's, so the distance from xn to x can't be any bigger than the diameter of Fn, less than epsilon. So xn goes to x. So since all we've used about the xn's is that they're a Cauchy sequence, we can conclude that all Cauchy sequences converge. And that is exactly what it means to be complete. So here is theorem 5.5.7. So let's let XD be a metric space. And I think I will just do this for XD is compact. And if you want to generalize to things that are like the real numbers, where every bounded subset of the real numbers is compact. If you want to generalize to metric spaces where all the closed bounded subsets are compact, I'll leave that as an exercise to the reader. So XD is compact if and only if. And let's install this condition star right from the start. If Fn is a sequence of sets and for all natural numbers n, we have the same 5 conditions. Fn is a subset of X. Actually, it's only going to be 4 conditions. Fn is not the empty set. Fn is closed. And Fn contains Fn plus 1. And we don't need that the diameter is going to 0 because we're not doing that part of Cantor's theorem. And we don't need to assume that the sets are bounded. If X is compact, then everything is bounded. We get that for free. And to show that it's compact, we need this to prove that X is bounded, which is part of proving that it's compact. We need this to work for all sets. Then we have that. The intersection of the Fn's is not the empty set. Let's prove this. So first, we're going to suppose that XD is indeed compact. Let's let Gn be X minus Fn. Then each Gn is open. And it's not hard to see that the GNs are an increasing sequence. If Fn is getting smaller, then everything that's left can only be getting bigger. All right. So G capital N is the union of the GNs from 1 to n, since it's an increasing sequence. Also, notice that X is not a subset of any Gn, not equal to Gn, because X minus Gn is Fn, which we assumed is not empty. So X is not contained in any finite union of GNs. But X is compact. If X is contained in any collection of open sets in their union, then it's got to be contained in some finite union. It's got to be contained, in this case, in the first n of them. We had a lemma like this in an earlier video. So that means that the GNs cannot be an open cover. If it was, it would have a finite subcover. We'd see it doesn't. But it's a collection of open sets, so the only way it cannot be an open cover is if X is not equal to the union of the GNs. So we have that X minus the union cannot be empty. That is not equal to the empty set. And then by De Morgan's law, that is the intersection of X minus Gn. And then the complement of the complement is just what you started out with. So this is exactly what we wanted. So our condition star holds. Suppose there was an implied pick a sequence Fn that satisfies all the given conditions, but I really didn't want to write this out. Anyway, let's go ahead and prove the converse. So we're going to suppose that the condition star holds. And we want to show that X is compact, and it's going to turn out that the best way to do that is by using one of our equivalent conditions. So let's let Xn be a sequence of points in X. And our big theorem, theorem 5.5.5, says that if all sequences have convergent subsequences, you gotta be compact. So we're just going to show that this sequence has a convergent subsequence. And we're going to build our ENs and FNs exactly as before. So as before, we've got that Fn is a subset of X. Fn is not the empty set. Fn is closed. And the E's are nested, so the Fn's are nested. And remember, the hard condition to prove was that the diameter is going to 0, and we have our condition star without the diameter going to 0, so we don't have to prove the hard thing. We've got the 4 conditions very easily. So then we're going to let X be a point in the intersection. Then by our condition star, X indeed exists. So X is in the closure of En for all n. And then by proposition 5.3.7, if R is positive and n is a natural number, then the ball centered at X of radius R intersected with En is not allowed to be the empty set. X is in the closure of En, so it might not be in En, but every ball around it has a point that's in En. Then now we're going to build our subsequence. Let N1 be a natural number such that Xn1 is in the ball centered at X of radius 1, and we'll intersect that with E1. And then we'll let N2 be such that Xn2, it's in the ball centered at X of radius 1/2, intersected with, now we'll take En1 and add 1 to it. And notice that Xn1, the first element of our subsequence is within 1 of X, the second element is within 1/2 of X, and so on and so forth. And also notice that if X is in En1, we can require that N2 be at least N1 plus 1. And let's let N sub k in a natural number be such that Xnk, it's in the ball centered at X of radius 1/k. So the Xnk's are obviously converging to X, and we can force Nk to be bigger than Nk minus 1 just by letting x and k be in ek minus 1 plus 1, and we can then require that nk be bigger than nk minus 1 plus 1. So the nk is an increasing sequence of integers, of natural numbers actually, so that means that the xnk's is a subsequence of the xn's. And it clearly converges to x. So we have that this sequence, and we didn't use any properties of it, so we must have that every sequence in x has a convergent subsequence. So what that means that by theorem 5.5.5, which is what we saw at the end of the last video, x is compact.